Good afternoon, my name is Zhang Haoxiang. I mainly work on the hardware side, focusing on UAV structure, sensor integration, and system reliability.
I am Hongping Chu. I focus on the software side, making sure all those sensors work together and turn data into decisions.
Today, we are excited to present Hermes Hybrid Environment Resilience Multi-Sensor Exploration System. UAV technology has advanced rapidly in recent years. However, when we look at platforms suitable for research and education, we notice there's a gap.
Many existing UAV platforms are powerful, but they are often hard to extend, hard to reproduce, and not fully open.
This limits systematic research on topics like multi-sensor fusion, autonomous navigations, and resilience explorations.
So we asked a simple question.
What if a research-grade multi-sensor UAV platform could be accessible by design?
That question led to Hermes, a low-cost, open-source, and highly replicable end-to-end UAV testbed.
Designed for resilience exploration, search and rescue research, and education. In real disaster scenario, one challenge is very common.
You often don't have a reliable prior map.
At the same time, high-resolution aerial imagery is become easier to obtain.
So in Hermes, we use aerial images and apply structure from motion to generate a coarse 3D environment model. This model is not perfect, but is sufficient for navigation and path planning research without prior field mapping.
Now let's take an overview of our system design.
At the core of Hermes is multi-sensor resilience, which is one of our key contributions.
Instead of relying on single sensing modality, we designed the system around three primary sensors: LiDAR, thermal, and RGB cameras.
Each sensor is paired with a dedicated perception pipeline, and the system adapts based on environmental conditions.
In our normal environment, the RGB camera takes the lead.
We use YOLO-based object detection to identify humans and project their locations onto the map.
This allowed Hermes to explore the environment and report where potential rescue targets are located.
When lighting conditions are degraded, the thermal camera takes over.
We extract Shotomashi corner feature, then track them using Lucas Canade optical flow.
By analyzing feature velocity and spatial distribution, we apply DB scan clustering to identify moving and high-temperature objects, such as humans.
In extreme environments such as high temperature or intense conditions, both RGB and thermal sensors may become unreliable, so Hermes fall back to LiDAR-based perception.
Using DB scan clustering on 3D LiDAR point clouds, the system performs basic obstacle detections, reports hazardous conditions, and navigates safely back if needed. This fallback mechanism is what makes Hermes resilient by design. Resilience also applies to localizations.
To support indoor and GPS-denied environments, we implement FastLeo2 and SLAM global localization.
LiDAR and IMU data are tightly coupled in FastLeo2 to produce high-frequency odometry and local maps.
A submap is extracted and later aligned with the global map using ICP-based localization.
The final SLAM pose is then fused and sent back to PX4 autopilot through the MapLink middleware.
With the EKF filter running on PX4, IMU drift is reduced and navigation stability is improved.
This makes localization more robust, more reliable, and suitable for future autonomous navigation.
As of November, we have completed the UAV hardware platform, sensor integration, software interface, and simulation environment.
Hermes provides a low-cost, replicable, and open-source multi-sensor UAV exploration platform.
Moving forward, we aim to further integration autonomy, strengthen resilience under extreme conditions,
and continue releasing components to support research and education. Thank you for your attention.